Hello, wonderful people of the internet. Welcome back to another episode of Leo's Labs MRS. Hey, thanks for coming in. I realize you're not able to follow the stream because you're at university, but yeah, thanks for being here anyway. Anyone else who might be lurking in chat, hey, thanks also for being here. Right, so as you can see from the title, we're actually doing something a little bit different today. Instead of focusing on ASCII art or photo mosaics, all this kind of stuff we were talking about yesterday, I'm actually taking a step back to talk about four-dimensional galaxy simulation. So let's talk about it and explain how this is even related to the stuff we were doing yesterday. Let's go to Zernal PP and just kind of write it all out. Okay, so yesterday we had a long discussion about ASCII graphics, ASCII art, and basically said this is composed of two different things, right? So one is the photo mosaic. Photo mosaic, that is the ability to take an image, block it out into a bunch of like kind of bigger pixels in a way, and then replace those bigger pixels with some sort of image tile, right? If you're going to do ASCII art, you kind of have to do the same problem, just with essentially a bunch of like colored tiles to some extent. The next thing, which is kind of a bit more challenging, is a structural problem. That is to say, if you have like some sort of object and you're trying to represent that in ASCII graphics, you're going to have to like transform the object a little bit so it fits into the ASCII shape. So for example, if you take a circle, well, when you turn that into ASCII, it's probably going to look more like an octagon or something like that. Maybe something like this, depending on your resolution and scale and all that kind of stuff. It might also just look like a square. And so this act of kind of taking your circle and transforming it into something that can fit into ASCII art is a challenging problem that could involve shape matching, I don't know, a bunch of really interesting questions as far as like optimization theory and stuff is concerned. That's the reason why I find this actually quite interesting. There's a lot of little research problems that can help like the entire area of computer graphics that are all kind of in this one toy problem that is turning an image into ASCII art. So we decided we would first tackle the photo mosaic problem yesterday. We went through a whole bunch of different papers and stuff that, I don't know, I thought were quite cool, talking about how to generate photo mosaics. And sure, we had a lot of different papers, we talked about a bunch of different things, but one way in which I wanted to try to tackle this photo mosaic issue was to find a fast implementation of color quantization. Right, and we started quantization... and we started a new package that was called Mosify, which stood for Mosaicify, like to turn an image into a mosaic, where we talked about, color quantization, and we were trying to implement that as kind of our first step towards getting any image into a mosaic. But as we started talking about color quantization, we started realizing that, okay, well, there isn't actually a good parallel implementation for color quantization. So parallel... color quantization, I'll just say CQ. So I started thinking about this more and more, and ultimately we realized, or I realized last night, that the reason why we don't have a good implementation for color quantization in parallel is because, quite frankly, the fundamental data structure that's useful for color quantization is the octree. Sure, you could use a KD tree or something like that, but it's fundamentally the octree, and this just is not optimized in parallel. So it's important then to take a look at other problems that might also have an octree in it, and one of those other problems is a galaxy simulator. Now, a while ago, we had the intention, myself and 3Blue1Brown, we had the intention of doing a four-dimensional galaxy simulation, which would basically involve creating a four-dimensional octree. So I don't know what that's called, but like whatever 16 tree or something like that. In order to do our 4D galaxy simulation. And yeah, that's kind of what we're going to work on. So the 4D galaxy, to me, seems like an easier problem than color quantization at this stage of the game. So we're going to be looking at papers in kind of similar areas, both of these different areas, seeing if we can, maybe hexadecatree could be it. But the point is, we're going to be basically looking at 4D Galaxy papers today and going through it, much like we were doing yesterday. I've mentioned this before, I mentioned this yesterday, but I really do enjoy going through papers. This kind of stuff is probably the most fun part of the job for me, just like literature review, reading papers, trying to figure out like how the methods work together, all this kind of stuff. It's quite fun. I really enjoy it. So I'm going to try to do as much as I can here live on stream. I might, again, not be able to stream for super long. Might be that we find a paper and I just need to take a step back, read it off the stream, and see what we can do there. So why exactly a 4D galaxy simulation? Why is this interesting, right? Okay, hey TS Jost, how are you? So let's say we have a two-dimensional galaxy, right? So all of these guys are planets or stars or some sort of object floating in space. Well, we'll say stars or something like that. So what you can say is that each of these objects is affected by all of the other objects in the grid. So this guy, for example, is affected by all of these points in here, but it's also affected, I guess I'll do this in dark blue, faintly, by these particles out here, right? That is to say that every single particle is affected by every single other particle in the simulation. This is, of course, very difficult to do because it means if you have n particles, then you have n squared operations that you have to deal with because every particle has to deal with every other particle. It's just a pain. So what people do instead of dealing with every single particle in the simulation is they split the grid up into something called a quad tree, where basically they split it up into fours and they split each one of these into fours and these into fours and these into four and this into four. And basically they keep splitting things into four like different grid cells until eventually each individual point has its own cell. Then they say, okay, this cell is located at this center of mass. So what every point sees, for example, let's say this point here, I guess I'll do this in light blue, we'll see this point, these points, and this point, but it will see just one giant glob over here, which is going to represent all of those points together. And so in this way, you can save on computational cost. And doing this is known as the Barnes hut simulation. Now, when we talk about color quantization, we basically do the same thing, except instead of being on a 2D spatial grid, you're on a 3D RGB grid. And then you basically cut things up based on that. Now, that naive implementation of color quantization, there are better ways to do it. And this is kind of where the question comes in. You know, the Barnes hut method is known for being a good way to, cut the space up spatially into, different quadrants or octants or whatever. And I guess my question is, what happens when you go higher to n dimensions? Let's say 4 dimensions to start, but ND. Obviously, this explodes exponentially because, you're going to have, a quad tree for 4 dimensions, an oct tree for 8 dimensions, a hexadecatree for 4 dimensions, and so on and so forth. As you go higher and higher, you get more and more octants and stuff to deal with, and it becomes a harder and harder problem to deal with. So how exactly do you scale this to ND? And the other question, which is kind of more related to the photomosaic and ASCII art stuff we were talking about yesterday, can we use some of these tools that we've learned from galaxy simulations to help us do a better color quantization scheme and basically create those buckets to work with our images? So that's kind of what we're looking at here. Now, the fundamental physics question, the reason why this is interesting is because if you take a 2-dimensional galaxy, or a 3-dimensional galaxy for that matter, and you allow it to just evolve in time with all of the little particles moving together, it will form a 2-dimensional disk. It will form a basically axis of rotation. That's really cool. We see it all the time. I mean, the Milky Way is a 2D disk. But the question is, if we have 3 dimensions of space to move in, why do we form a 2D disk? And the reason is because, the axes of rotation are fundamentally 2D. But in 4 dimensions, you don't only have one disk of rotation, you have 2 disks of rotation. You can, for example, rotate along the X, Y, and ZW planes at the same time. And so because of that, the question is, do you get 2 rotating disks? Do you get maybe some sort of 4D, what happens in 4D? Do you get 1 disk? Do you get 2 disks? Do you get no disks because the forces of gravity work different in 4D? I don't know. These are all questions that we have. Spacetronauts, todo bien, gracias, y tú? Así. Let's see. This Saturday, I'm volunteering to help the Cinderella costumes department finish up all the preparations before the show starts the week after next. And in 10 minutes, I'll leave to make breakfast. Hope you all are doing well. Yeah, I'm happy to hear you're enjoying the stage performance stuff. Thespianisms. I actually don't remember what it's called, but theater production stuff. It seems like you're really enjoying it. And yeah, good luck, like T.S. Jost said. Okay, so I think, we're just going to hop into the literature and see what we can find. I was looking it up some this morning. Okay, well, let me actually first go to Discord over here. So we've got a channel in Discord known as a paper pile, which is basically just me posting papers that I find are interesting. And so yesterday I put these papers here for the color quantization stuff. Tech Theater seems to be the name for it. Yeah, okay, fair enough. But yeah, I hope you enjoy it. But I also found a bunch of other papers that were quite interesting. So for example, this one, Copy link. Let's go over here and let's take a look at this one. Paste it over here. Give it a second. So I found a paper for automatic portrait image pixelization. Are you gonna? There we are. Which essentially, let me see if I can find the images here. You gonna? Okay, give me a second. All right. It's not letting me see all of the images, I don't think. But essentially what it's doing, let me see if I can download this image here. Essentially what it's doing is it's taking an image and turning it into like an 8-bit ASCII, not even like 16-bit, whatever, 32-bit ASCII, I don't really know. But that's all it is. And this is like published in 2021. And I'm like, really? I feel like, I don't know, I was quite surprised to see this in 2021, right? Because this is something that, people have been able to do since 1970s. It's not particularly challenging to do. So I was kind of interested to see what they did that was different than everyone else's. And then I started going down the path of wondering hey, is there something that we could do to kind of, I don't know, make some sort of 3D voxel art with something like this. And then maybe do it in Minecraft. I don't know. There were a bunch of things like that kind of came to mind, and I thought about maybe looking at, but I don't think we're going to do it in the end. I'll be on Lightboard, the best seat in the house with the worst audio because I'm on headset. That's probably fair. Okay, so this is a paper I found yesterday, but also I found a bunch of other papers. I think I pasted them in here as well. Let's go copy link over here. There, paste. Sorry, but I missed the color quantization stream. How do you end up using octrees for this problem? Ignore off topic at the moment. Yeah, give me a second. So it's actually remarkably straightforward. So I say that, but I say that for everything. So let's say we have an RGB color space. I'll do this in white, I guess. RGB color space. Now, I don't have 3 dimensions to represent this in. So let's just take the R and B dimensions here. So let me draw a graph really quick. And we're going to do R over here and B over here, right? So if we take an image, it doesn't matter what the image is, it could have a lot of blue particles, right? Or some kind of blue and red particles, or some red particles, or stuff that's kind of black over here, right? So you have a bunch of particles that are different colors on the grid. So you basically take every pixel and you throw it into RGB space. So this is a fundamentally different space than the image. So for example, if the image is, let's say this is the image, just like blue, then there's a black dot here. Wow, I guess I'll do that in white. So there's a black dot here, and then there's a red dot here, and then there's a pink dot here or something. Then the pink dots would go somewhere in the middle here to this range over here. The blue dot would go over here. The red dot would go over here. And then the black dot would go over here, right? So after doing this, what you then do is you take the grid and you split it up into quadrants. Again, in 3D, these are going to be octants because you also have green to deal with. But basically, you keep splitting these guys up until each one has their own box, essentially. Let's just split it like this, and that. 1 second. And here, something like this. Again, I'm just kind of doing a really rough split here. There, here, and here. Okay. So what this does is it makes it so each big box, let's say this box in here, can have a constituent color to represent this big box. So this could be mostly reddish. So this big box is represented by this red color. And again, this pink box over here is represented by this pink color over here. And this blue one is represented by the blue color. And then we have the black one over here represented by the black color, right? And so what you do then is you kind of say, okay, well, in this picture, we have red, pink, blue, black, and these are kind of what we're dealing with, right? But then you can go one step deeper. So not only do you need the first stage where it's just red, pink, blue, and black, but you can go a bit deeper where you have, these elements in here, which are mostly pink, but kind of a little bit black, maybe a little bit blue if you go, this direction down here. And so it's a mix between blue and pink. So essentially what you're doing is you're taking the image and you're splitting it up into all possible colors, and then you're averaging colors that are close together. And the way in which you're averaging those colors that are close together is by basically splitting the space up into octants and saying all the particles that belong to this octant are now going to be all colored as this color. So if you have something that's kind of in the middle between blue and red, it's going to be pink. But if you have something that's, kind of in the middle between pink and blue, it's going to be either cast to pink or blue. So this means that you're minimizing the number of colors, you're quantizing the number of colors, and you're basically casting an image that was before, 256 colors onto something that is 4 or 8 or 16 or 32 or something like that, depending on the number of boxes that you choose. Now, there's a bunch of different ways to choose these boxes and stuff like that, but ultimately you end up with images that look something like this. So I'll show it to you right now. CD Projekt, Mozify, LS, Mirage, Pride, .jpg. So here is a Pride flag I grabbed from the internet. I was trying to think of something colorful that we can easily quantize. Let's just go here. So here you have all the colors. And then if we go down here, so here's a quantized color. So here I switch it so we only have 8 colors available. Now, I'm not saying these are the perfect 8 colors. There might have been something wrong with the implementation, but you can clearly see here that, there isn't as much detail. You've cast all of the red and orange kind of together into the same color, all this kind of stuff. So here was the original image. Here's the color quantized image. They're both the same size. I don't know why my editor is showing them in 2 different colors, but basically that's what you're doing. You're just quantizing the colors in this way. And again, as I said before, this is the same fundamental problem with Galaxy simulation. Just because you're splitting the grid up into into octants or quadrants in order to minimize your computation in some form, and it's kind of the same problem. Which is why there are a whole bunch of really interesting color quantization papers that came out, and the question is, how much does this literature bleed into each other? Can we use the Galaxy simulation stuff for color quantization? Can we do the color quantization stuff for Galaxy simulation? I don't know, but getting a good parallel implementation for Galaxy simulation would be pretty cool. So I suspect that where this is going to go is ultimately finding a way to more accurately represent Galaxy simulations with color quantization methods, because I suspect that the color quantization methods are a bit more, I'm going to say more robust, because probably more people are used to that problem, and in particular the computer graphics literature is more used to the problem, and the computer graphics people are the people who have GPUs, which are good for parallel processing. So my guess is that the color quantization literature is going to be a little bit better than the Galaxy simulation literature. But that's what today is for. We're going to kind of try to find a plan of attack here. Like I said before, and here's just for the record, even though today I labeled the stream as 4D Galaxy simulations, that's your journal new page before, there's actually a whole bunch of related problems here that we're trying to work towards, right? So we have the 4D galaxies, then we have photo mosaics, then we have ASCII art, video, I guess what I'll say. Then after all that's done, we then also have fractal compression. And then we go back to physics for a method to solve physics simulations, sims on fractal grids, which we'll get to that one later. But ultimately, this kind of bleeds into each other, right? So, we need the 4D galaxies. So this problem and this problem are very closely related because of octrees. And then this fundamentally creates or is a fundamental building block for the ASCII video, because it's one of the core components of creating good ASCII art. So both of these bleed into this one. And then once that's done, this guy immediately turns into fractal compression, because at that stage, we should be able to understand how to essentially deal with large affine maps is what we're going to try to do. And then after we deal with large affine maps, and we have an idea of how to do fractal compression slightly better using the fractal flame method, all this kind of stuff, then we can finally use the fractal compression methods for the physics simulations. So even though it seems like they're kind of all unrelated, they're actually kind of the same problem, all just cast under a different light. And so this is one of those things where, as you start reading more and more, and specifically in different interdisciplinary fields, you start to see oh, hey, this thing is literally the same as this thing, and these people don't talk to each other. Therefore, there's going to be a lot of overlap that a lot of people have missed in the literature and stuff like that. And this is kind of what I'm looking for, right? When it comes down to it, I've mentioned this a lot before, but I don't feel like research is so much about following the scientific method super rigorously. In my opinion, research is also about reading the literature and trying to figure out like where gaps exist, where people haven't really thought of this and that, where you could apply this particular technique to that particular area. And to me, that's some of the most interesting stuff to do. So this is kind of what we're looking at right now. One second. I just realized something, and I don't exactly know why, but my audio output capture for Pulse Audio is not working, which is weird, and I don't know how to fix that. Let me see, jack sync Pulse Audio, HDMI, no, input devices? Weird. Okay, so you guys can't hear any of my desktop notifications, which makes it kind of makes sense a bit. Let me see if I can figure this out. So this is recording, and what we want, okay, so then what we want is this one? No, that's bad. If you guys don't mind, let me be right back. I'm going to turn stream off, and then I'll be right back. Give me just 2 seconds. Sorry about that. By the way, Hendo, the AV guy, thank you so much for following. Really appreciate it.